Hey, everybody. So we're going to continue talking about probability. We're still doing some of the pretty basic ideas, but we're going to start to complicate things just a little bit. So let's jump right to it. I want to define a couple of things, and we'll do a couple of examples. I think this one will be pretty short. Okay. So I started by considering the following experiment, and I've already written out the experiment in the sample space. It's a smaller version of one I showed in a previous video, the results from. This is, so imagine I have three four-sided die. So they've each got the numbers 1 through 4 on them. There's a red, a blue, and a yellow. And let's assume everything is fair, meaning there's no preferred color or no preferred number, that everything has the same likelihood. You're going to reach into some kind of bucket, pull out one of the die, and you have the same likelihood of pulling the red, blue, or yellow. And then you have the same likelihood of rolling a 1, 2, 3, or 4 once you pull that, okay? So just as a reminder, we'll do a couple of basic ideas. For instance, I might ask the question, what is the probability I pull a red die, right? So it's pretty obvious, I think, in this case, but let's go through some of the formal notation and things so we can start getting used to it. Typically what we do is we name an event. So I'm going to name the event pull a red die. And I ask probability questions by writing P of that event. Okay, that was the notation. I introduced that way. So this sentence here represents, or this collection of symbols represents the sentence, the probability I pull a red die. Okay, that's what this, and it is in fact a number. We just don't know what the number is yet, but that's what those collection of symbols are. So then to figure out the number, right, remember our rule, we take the number of events in R. So each of these is an event, right? Pulling the red, rolling a 1, pulling the red, rolling a 2, pulling the yellow, rolling a 3, right? So there's 4 events with red. There's a total of 12 events. If I want to reduce it, I can have 1/3, right? And I think we probably understood that. There's 3 marbles. I've got a 1/3 chance of pulling the red, but we see it shake out from this idea of drawing our sample spaces, counting, all that kind of stuff, right? Obviously, this is more work than we probably needed to do this. The point of this right now is we're trying to learn how to use this notation, because pretty soon it's going to be more complicated, and having powerful notation at our disposal is going to become very important. Okay, let's try another event. Let's name an event. How about E, roll an even number. And let's ask the probability of E. Okay, so we just look through our events and count how many of them have even numbers, or our outcomes, how many of them have even numbers rolled. So 1, 2, 3, 4, 5, 6, and there's still a total of 12 in the sample space. Okay, so simple enough. That's what we were doing last time. However, let's begin complicating things a little bit. These are both pretty simple events, right? This one is only concerned with pulling the red die. This one's only concerned with rolling an even number, right? It doesn't care what color. This one doesn't care what number gets rolled. But often we have events that are more complicated, right? So let's now complicate these events. And the first 2 ways we typically complicate things is we're going to use and or, right? So for instance, I can write R or E. Okay, this is a new event, right? It's all of the outcomes that have pull red die or roll an even number. Okay. When we use or, we include the times that both of these things happen. Okay, so it's not only one of them happening. It's either of these things happening or possibly both. So in this case, then we can ask the probability of R or E. We have to count, right? There are still 4 events where there are reds pulled. Let's mark the events where there's evens pulled. Right? And then I just count how many events there are in combination. Notice that some of them got counted twice. We're not going to count them twice. So there's 1, 2, 3, 4, 5, 6, 7, 8. 8 out of 12. So we expect that 8 out of 12 times we will pull a red die or roll an even number, including the times that we happen to pull a red and roll an even number, right? That can happen. So this is our or event, right? And that's what they are. They're events. An outcome is in an or event if it's in either of the events. So let me say this really clearly. An or event is a combination of 2 events, right? And an outcome is in the or event if it's in either of the events it's built out of, including the case where it's in both of them. Okay, so just what we did here. Here's another way we combine events. How about R and E? Okay. This is that we pull a red die and roll an even number. Okay? So now the outcomes that we count have to be in both of the original events. We only count outcomes where we are rolling the red die and, right, we are pulling the red die and rolling an even number. So when we ask the probability of R and E, right, we're now only going to be counting these 2 events here, right? These 2 events here that have both a red die and an even number. So there are now 2 out of 12 or 1/6. Okay. Notice the and event is smaller than both of these. The probability of the and event happening is smaller than the probability of both events happening on their own. The or event is larger than each of these, right? That's typical. Sometimes they can be equal, but that's typical that and events tend to have smaller probabilities, or events tend to have larger probabilities. It's harder to do 2 things, right? When I said this event, you had to accomplish 2 things. There's 2 places where it can go wrong. You can reach in and not get a red die, but then even if you accomplish that part, you might roll an odd number and you don't get to do it, right? So there's 2 places for it to go wrong. Whereas here, it's kind of the opposite. Like, oh, I pulled the yellow die. I didn't pull the red one, but I still have a chance to roll an even number. So we're still having a chance to satisfy this, even if part of it goes wrong, where the reverse is true here. So that's why they tend to be small, and the other ones, the or events, tend to be larger. Okay, so we'll see more of these in some coming videos. I'm just introducing them now. There's a couple more notations I want to give. We have this notation. Let's call it the complement of an event. So I'll use the event R, written. We'll tend to use this one, right? Sometimes people say R prime or not R. There's a few other notations. You'll probably see me use this. I've used this one in the past. I'll try to stick with this one. I think this is what the book uses mostly, but I'll probably slip up and use that a couple times, R complement. Or you'll even see this sometimes, this little not symbol. But I'll try to stick with this one. But all the complement means is all of the other stuff, all the outcomes not in R, right? If an outcome is in R, it's not in not R, and if an outcome's not in R, it is in not R, if that's not too confusing of a sentence. So in this case, right, the probability, so R complement or R prime is not pulling a red die. Right? So the probability of R prime in this case, so if we look back up here, we're just counting all the times. I don't want to make this too messy, right? It's everything, but these are the 4 where red's pulled. So the rest, the other 8, are the probability. We get 8 out of 12 is the probability of not R. Okay, and there's a nice little fact sitting here in front of us. If I take P of R plus P of not R, or R complement, let's do it with the unreduced fractions just to make things a little bit clearer, I think. Right? What do we get? 12 twelfths or 1. This is always the case. If you add two complement, if you add the probability of an event and the probability of its complement together, you always get 1. You're saying, what's the probability of this thing happening, or what's the probability of it not happening? One of those two things is going to happen. Anything I do, one of you're splitting the probability, the outcomes in half, or not necessarily in half, into 2 groups. One group is larger than the other sometimes, like in this case. But one of those 2 things has to happen, R or not R. There's no way around it, right? Look at what's happening here with our fraction. They're both going to have the sample space in the denominator of 12. R is going to be some of them, not R is the rest of them. So you're always going to get the total of 12 in the numerator when you add them together. So this is a fact about complements that is very useful, right? So in general, we could say something like, for an event A, P of A plus P of not A is equal to 1. Sometimes we write this as P of A equals 1 minus P of not A, right? And the reason for this is we will find things a little later where sometimes we want to know the probability of A happening. It's easier to find out the probability of not A happening. So you can discover this number much easier than you can discover this one, and then you simply subtract it from 1. So we will see we'll see a decent amount of events like that in the future. Okay, so in some later exercises, I won't go into much more detail about that here, but I'll remind us of that when we get there. Okay. All right, let's add one more kind of thing to this. I want to keep my sample space here, and I'm going to use these same events, so I'll do it here. Okay. So we're going to add one more kind of probability with a new notation. This is something called conditional probability. And the way we say it, or let's do the symbol first. We write this, P of, and as usual, this is our probability of an event. And the kind of event we have here, again, is we're combining other events to make a new event, but it's a little different how we combine it here. We write this symbol. I have A is my first event. I write a vertical bar, B, okay? And the way we say this is the probability of A given B. Okay? In other words, it's the probability that A will happen if we already know that B has happened, right? The fact that B has happened or B exists or whatever, it's hard to, this is very general and abstract right now. We'll do some examples in a second. But the fact of B is more information, and so that helps us. It gives us more information so that we can get a better estimate on A, right? Or it changes the conditions is another way to say it. What we'll see is it actually reduces the sample space. That's another good way to think about this. So let me give you a formula for figuring this out first. Though we don't always have to use this, and we're about to do some examples without using it, but then we'll see that it matches up. The probability of A given B is equal to the probability of A and B divided by the probability of B. Okay? So that is our mathematical definition of this kind of probability. So let's do this with these two events just to see how it works. So first of all, I'll just do the probability of E given R. Okay. So in this case, we have, so let's think about what this is saying. This is the probability of rolling an even number given I pulled a red die. Okay. Now we can probably guess what this should be. Let's do it first by just looking at our sample space. Our sample space is all of these numbers if we're asking a question like, what's the probability of rolling an even number? However, we have extra information. The information is, I already did the first part of the experiment. I've pulled a red out, right? So now my sample space has been reduced. These two columns, the blue and the yellow, are no longer possible, right? So I'm only in this sample space, okay? And here, I can just count out of these four, there's 2 even possibilities out of 4, which gives me 1/2, which is actually the same in this case. So this is a case where it actually didn't make much difference. This is pretty clear to think about, I think, since all of these dice are the same, the probability of rolling an even number is the same on each one, right? They all have 2 out of 4. Okay? Let's change this experiment a little bit and see what happens, that sometimes these conditional probabilities don't work out the same. Let's say, for instance, let's say these dice are not, let's just draw a new sample space. Let's say the dice are not all 4-sided. Let's say the red has 4 sides. The blue has 3 sides. And the yellow has 2 sides. Right? You might be asking how we can get 2-sided dice. There are some odd shapes that you can make with curved sides and things like that. Or an even easier way is you could have something like a 4-sided die, but every other side has the same number on it. So there's really only 2 numbers that you can roll. So that's kind of one way to get 2-sided die. But in any event, let's say that that's what we have. Our sample space looks a little different now in this experiment. Red 1, red 2, red 3, red 4, blue 1, blue 2, blue 3, yellow 1, yellow 2, right? Those are all the things that can happen, right? Depending on which die I pull out, I get a different options for the numbers that I could roll. So this is no longer valid. So now, let's try to do this E given R. So now, what's the probability of rolling an even number given that I pulled the red die? We see, actually, let's do the probability of E first. Let's do a couple of things first before we get to that, and then we'll see where this is all heading up to. So let's do the probability of E. What's the probability of rolling an an even number with this new construction for this experiment, right? So we look at our sample space, we count all the even number rolls. I count 1, 2, 3, 4. We've got 4 out of how many options are in our samples, how many outcomes in our sample space? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've got 4 out of 9 is the probability of rolling an even number, right, in this case. Then let's look at the probability of rolling an even number given we rolled a red. So now I know that I've rolled a red die. These 2 columns are no longer in the sample space. We've reduced the sample space. This is what conditional probability does. And there are 2 even numbers out of the total of 4, or 1/2. right? So in this case, the probability of rolling the even number originally is a little less than half. If we know we rolled the red die, our chance goes up a little bit, right? And that makes sense. If you look at these die, the way they're set up, the red die or the blue die has fewer even numbers, a lower ratio of even numbers, right? It's only got 1/3 even numbers versus 1/2 even numbers for all these. So when we've got this one's a little worse for getting evens. When that's still in the mix, it makes it harder for us to roll an even. But by knowing that it's no longer in the mix, our odds go up. We've removed both of these die and we're left with a die that has a higher percentage of evens than the ones we removed. So our odds get a little bit better. Let's finally compare this using the formula that I gave you a minute ago, which is the probability. Even though we already computed it, let's see how that formula works. Remember, this formula was the probability of E and R over the probability of E. So I'm going to compute the probability of E and R. We already computed the probability of E here. So the probability of E and R, that's rolling an even and drawing red. We've got 4 red, and of those 2 are even. So these are the only 2 outcomes in this sample space that are both a red die and an even number. So that's 2 out of 9. Okay. So the probability of E and R, 2 out of 9. The probability of E is 4 out of 9. Right. How do we divide fractions like this? We multiply the numerator by the reciprocal of the denominator. Notice what happens. These 9s cancel. We get 2 out of 4, exactly the same number we saw over here, which reduces in the same way. So using that formula, we still get the same results. Okay, so that is conditional probability. We'll do some other videos on this in a little bit. We're going to add some ideas that might make them, give them some more interesting examples. I want to do one more example with conditional probability in this video, though, and I want to do this using, let's look at some data on a spreadsheet. So let's see, open this up. There you are. All right, so here's the situation I invented over here. So I got this data. There's a source on it, just some weather site that gives the average number of rainy days in each month. Okay, I forget their precise definition, if there was some minimum amount of precipitation that had to happen or something like that. They had some definition of what constitutes a rainy day. But anyways, we can see the number of rainy days laid out here in Seattle, average per month, right? So suppose you were planning a wedding, right? And you wanted to get married in Seattle. So let's create a couple of events. Let's call, ooh, that's too big. R is equal to a rainy wedding day. Okay. And we might ask ourselves, what is, this thing is being jumpy today. Some days it seems to work better than others. What is the probability that if you plan a wedding in Seattle, let's maybe say rainy wedding day in Seattle, right? What is the probability that it's going to rain on your wedding, right? Well, all I did to compute this is there's 152 days on average of rain out of the 365 possible days, right? And that comes out to be 0.416. Sorry, these are such messy letters. Some days I seem to be a little better with this thing than others, okay? So you would say you have about a 42% chance of having rain on your wedding day. However, most people don't plan their wedding during the rainy season, right? And so if the question isn't what's the probability of if you plan your wedding on some random day during the year that you'll have a rainy wedding day, this would answer that question. However, maybe you've already got a place booked and your wedding date, let's say this, your wedding date is in August. Right? So now the question to ask is, what's the probability that there is rain on your wedding day given the wedding date is in August, right? So now we've reduced our sample space. We only care about the 4.8 days of rain out of the 31 days in August, right? So this is this idea that we have reduced the sample space. Right? So let's compute this. We would look over here and see there are 4.8 days of rain out of the 31 days in August, right? And I just worked that out and I get 0.155, right? So now all of a sudden your odds are a lot better, right? Instead of 42% chance of rain, there's only a 15% chance or 15.5% chance of rain, right? So that extra information, knowing when the wedding date was, changed the situation for us, okay? And like all conditional probabilities, that it reduced the sample space, okay? Let's look at this one more way with that formula we had a second ago. So this should be the probability of R, oops, that says and, sorry about that, R and A divided by the probability of A, right? So let's think about how we would compute this. This is the probability that a random day is both rainy and in August, right? Well, we look up here and we see on average there are 4.8 rainy days in August out of the 365 days of the year. And then the bottom is supposed to be the probability that a random day, if we picked a random day on the calendar that it's in August, well, it's 31 out of 365 days. There's 31 August dates out of 365. Again, to figure this out, we multiply by the reciprocal of the denominator, and we see what's going to happen. The 365s are going to cancel, and we end up with the exact same fraction we kind of worked out by thinking it through up here, right? Which again will be the 0.155. Okay. All right, so that is it for the introduction on probability. We'll get into some deeper ideas in some of the later, in some of the next videos. Okay, everybody, see you next time.